Okay, now today we'll continue from last time. Who remember where we stopped last time? Saya punya kamera part ni yang paling cerah boleh buat. Tu pun saya pasang lampu, berpindah mata ni. So, anybody know? Where did we stop last time? Nobody remembers.
Thermal effect.
Thermal effect, okay. Thermal effect, okay, that one I touched. If you want to know a bit more detail on thermal effect, you can watch the YouTube video in my channel on 8th of July 2020 from minit 20 hingga minit 44. That is where there more detailed explanation and some drawing. Okay, so saya tak explain this time, so you can just watch in the YouTube minit 20 hingga 44. Alright, and then you can ask me questions if you don't understand. So next year lah, let's go to my iPad. Allah, macam lagi is quiet. Itu ni. Something here, sorry, dia stop lagi. Can you see? Nampak?
Yes, madam.
Tak ber clear? Apa? Tak dengar.
Nampak dia, nampak.
Okay, so we talk about thermal runaway, but detail drawing for the BJT, you can watch the video if you're interested. Okay, base resistance. Now we want to talk about base resistance and apa nama ni, or the other name is emitter crowding. It's the same mechanism, tapi nama kadang-kadang sometimes we use the name of base resistance effect, sometimes we use the emitter crowding effect. Ini, okay, kalau baca textbook dia akan ada macam-macam, ada kadang pakai nama tu, nama ni, it means the same. So okay, this is a BJT, okay, where you have this is the base, this is the emitter, and this is the collector. There are dua base either side. This is normal, the easiest, design for BJT. Yang kalau kita nak buat kuih lapis, we want to fabricate it. This is the simplest design. However, this simplest design have limitation. Okay, the limitation is what we're going to explain, which is what we call the base resistance effect. Now, how does it work? The emitter. Okay, so okay, when you forward bias, if you operate the BJT in forward active mode, what happens is, what do you do to the base emitter junction? How do you bias the base emitter junction if it's forward active mode?
Forward bias.
Yes, you forward bias, right? So you forward bias. Is there a lot of current or little current if you forward bias?
A lot.
A lot. Forward bias always a lot lah kan. So saja je saya tanya, we tidur. So jadi we have a lot. So it means that this is the emitter. So this, let's say NPN, and this is N, and P, N. Okay, it's a NPN. So basically, if I were to draw, macam dia ada P kat sini, N kat sini, itu kan. Betul. So so if I can draw the diode, it looks like that, and it's all over. It's all over. Sini. Saya tak draw banyak lah sebabnya it's a lot of diode connecting the base, the emitter to the base, and so on. And the same goes to the downhill. Tapi yang kita nak concentrate is the base to emitter. Okay, so now okay, we have a lot of, it means that you will have a lot of current flowing. So you have a lot of current flowing here to here to here. Okay, so but the contact is from the outside, contact is over here. Emitter kat sini. And we know if you want to make the beta, the gain high, how do we dope the base compared to the emitter? What's the relative doping of the base to the emitter if you want to make the gain to be high?
Need to be higher doping.
For which one?
For the emitter.
Yes, emitter you make it high dope. You want more free carriers because you want higher current. However, for the base, you make it low dope because
we want the base current to be low.
Why?
Because gain is IC over IE, beta. Right.
No, the answer is because we want to reduce the recombination, right, in the base. Betul tak? That's the answer. Because we want to reduce the recombination in the base. Because if you reduce the recombination in the base, therefore the base current will reduce. So therefore, optimized design, we increase the dope of the doping of the emitter is high, the base doping is low. What happens when the doping is low for a semiconductor to the resistance? Is it high or low? What happens to the resistance of a semiconductor when the doping is low? Is the resistance high or the resistance low when the doping is low? You understand my question? What's the answer?
The resistance will be higher.
Why?
Because if we put more doping, then we already move the Fermi level. We either move Fermi level, make it easier to pass either electron or.
Okay, the higher the lower the doping, therefore there will be less free carrier. So therefore if you do it will make the material to be higher resistance. It seems like a higher resistance because less free carrier inside the material. Therefore, so the base, let's go back to the so now you know where I live. I live in the Wi-Fi. Maybe better password, please. Okay, so so the base resistance is So the base doping is low, therefore the resistance is high. So area yang ni, saya draw, area base ni, color copy. Ni area base lah. This base area is actually having a high resistance. Okay, so now the problem, and now we have an emitter with a low resistance, base with a high resistance. The current, okay, when we forward bias base to emitter junction, it means there will be a lot of current flowing. Where is the path of the current? Okay, so where is the path of the current? So let's. Saya nak buang tu, okay, saya nak buang warna kuning. Where is the path of the current? So warna hijau lah. So the current will move from positive to negative, right? So this forward bias, the current will go there. If this then current will go here through the diode. So each diode, it will go through the diode, right? Saya tak draw banyak diode, tapi macam gitulah. Lebih kurang. So ada yang akan pergi macam ni, akan macam ni. So okay, because there's a two base at the either side, yang ni pun akan pergi macam ni. Okay, current is like water. Current is like water. You always want to go to the nearest, the easiest path. It means that the less resistance. Dia akan pergi ke the less resistance. For example, if you have a current from here, it will go through here. It will go here. It will not go there. No, it will find the lowest part of resistance. So, however, if you can see here, because the base contact is at either side, can you imagine at the middle here? You have high current or low current? The current at the junction here is high or low compared to, saya tulis sikit, tanya soalan lah. So we have A, region A, region B, region C. Okay, A, B, and C. Which region has the highest current? Which PN junction region? Sebab setiap satu A, B, and C ni dia ada PN junction, so ada diode. Which gives you the highest current?
AC.
Okay, Afiq jawab A and C. The rest of you? Jangan tiru tau. Kalau tiru saya akan tanya kenapa. So you need to think first. Why? Okay, who wants to answer? Mana Muhaimin?
Yes, madam.
Apa jawapan awak?
ANC.
ANC juga. Kenapa ANC?
Sebab ANC is more easier compared to the B.
Okay, so A and C will have higher current, right? Or to B. Now, the problem is when you have, so now if you have a lot of, katalah ada 10 current, so majority of the current will concentrate in A and C and not in the B area, right? Right. It means that when we design the BJT before, we assume that it's constant. When we design, bila kita calculate, you calculate doing, remember in your first year, the emitter current, the base current. When we do the calculation, we assume all are uniform, but actually it's not. So actually the current distribution is not the same. Therefore, at this A and C region, we have a problem where the current will be high, right? And another thing, because the base resistance, the voltage drop will be close to IR, right? As you go further from the base to the, or you go further from the base to the emitter, diode junction tu, the resistance will be higher because it has to go through the base longer, right? Any shorter route, it means that less resistance has to go through. The longer it is, it means that it has more resistance to go through. You can imagine it like macam setiap satunya ada resistance macam itu. Yang ni ada satu je resistance. So in order to go to the base, you have to go 1, 2, 3, 4 resistance. Macam tu lah. 4 resistance. So therefore, so the base resistance makes the, the base resistance makes the ununiform of the current, which gives rise to the effect that we call emitter crowding. Emitter crowding means the current is crowded at a certain location or a certain space, which means that the current are crowded at A and C. What happens when a lot of current is tertumpu, localized in one small region? If a lot of current flowing in a small region, what will happen? Anybody?
Saturation.
What do you mean by saturation? No? Okay. Think about the current density. Okay, I'm giving a clue on current density. What happens when the current density is high? Haris? What do you think? What happens when the current density is high?
I'm not.
You're not? What?
I'm not sure.
Okay, I'm giving an example. This is current density. You have two wires. Okay, you have two wires, and one wire is big in terms of diameter, and the other, so this is A, and this is B, wire B. So, but both are carrying the same amount of current. So means 10 amp going through here, 10 milliamp. This is 10 milliamp. What do you think? Okay, let's say we increase to 100 milliamp. What happens to, what's the difference in that will happen to A and B? Soalan saya yang tak jelas. Alamak. You understand my question?
Yes. Current would pass through A much faster compared to B.
Much faster. Velocity doesn't depend on the area. The velocity depends on the speed of the carrier and the scattering rate. I don't think so. So what will happen is that I give you another like extreme example. If I put a 1000 amp to A and 1000 amp to B, which one will damage first?
B would damage first.
B,
Why?
because there's more load on the wire. The wire can withstand the current because it's thin.
Because the current density is very high. Okay, so although the current is the same, but the current density is actually for B is very high. Okay, so it cannot, when the current density is very high, we have a heating problem. So the I squared R is based on the localized on the density. So in this case, right? In this case, what happens as the emitter crowding in A and C? When you have emitter crowding in A and C, what happens is you have a very high current density. And if the current density you keep on increasing VBE, because you want to increase the IC, you increase the VBE. You increase the base to emitter voltage, therefore you get higher emitter current. when you increase more of the voltage, it means that more loss will occur here, more loss in the base, and therefore more current will go to the ANC. So the effect is even worse at higher voltages because you will lose more of the voltage drop over here, because voltage drop is V equals to IR. So when the current is bigger, the drop will be more. So the what do you call it, the diode on the A and C will turn on more and will carry more current, which then will give rise to emitter crowding, which gives rise to heating. Okay, so because you have a very high current in a small place, and if the current is at a small place, it will damage this area. It will burn basically lah. So the heat, when the heat is very high, so you will see that actually this area will burn. Okay, it will damage the transistor. So this is not good. Number one, it will damage. That is in worst case scenario. But if you look at this graph, IC versus VBE, you increase the VBE voltage, right? This is just a diode current. It's supposed to be a linear like this. But because of the base, because of the base resistance, you can see it's banded. You have less because here this is due to the voltage drop in the base. So the amount of voltage you put are lost due to heat, which is not good. We want all the voltage used to create diffusion current. But instead, the voltage that you put have been lost in the base emitter region over here, right? Therefore, so to conclude, base resistance or emitter crowding is a problem because of the design of the base current, base region have to be low dope. So we engineers have to solve this. So to solve this problem, not over here, you can Google. To solve this problem, they do fingering. Fingering means when they design the base, so like this. So the design something like that. So the base has more contact, so the emitter will be here. So which means that what you are doing, you are increasing the closer the contact to the emitter. So tak ada dah yang it has to go to very far by fingering. So you can see the base to emitter is very, so the base to emitter contact is very close everywhere, base emitter. Okay, so this is an example to show you that whenever we have any design problem, and the engineer has to find a solution to solve it. So if we need creativity to solve it, so we cannot increase the base doping. To solve the base emitter problem, actually the easiest is you increase the base doping. However, it doesn't help because you will have a problem to the gain. So what happens is smart engineers do research and they make this fingering and it solves the base emitter problem. So it's like they make fingering, or ataupun nama lain dia interdigitated comb-like base emitter contacts are used. Okay, nama lain fingering ni interdigitated comb-like base. So dia design dia punya contact tu macam ni. Any question? Faham tak? So saya cerita tu tak jelas.
No, it's quite clear.
Okay.
Does it also call fin type BJT?
FIN, FIN.
Yeah.
Okay, there are many names, so if you can Google this to learn more. Okay, that's on this. So this shows that whenever when we design something, as an engineer, you will face problems later when you work. So we need to find creative ways or intelligent ways to solve it, to ensure that the no more new problem that will occur. For example, so that is one example of a smart way to reduce the effect of base resistance of emitter crowding effect. Okay, there are also other things. That's why there are a lot of research to solve problems. Okay, next ialah okay, Afiq, you can switch off. All your internet is not okay. Out semua dekat UIA. Oh, UIA ada internet problem sekarang?
The internet sometimes is like very flaky, so it's not really stable.
Itulah saya pun dengar ada orang complain. Tapi you should complain. You know that the form kan nak complain internet tak okay. You know that?
Yes, I know. But when I want to complain, the internet was stable for the time being.
Complain lah sekarang. Tapi kalau tak apa, awak kena jot dan pukul berapa and berapa lama. So when you complain, you need to, because if nobody complain, they won't do anything. And generally I heard now ramai orang complain. Tapi dia complain tak buat apa-apa. So the university say, see, nobody complain. There's no problem. Awak je sibuk lecturer kata tak ada masalah. Right? So you need to collectively complain. Tulis kat situ pukul berapa sampai pukul berapa, what happened. Okay. Sebab macam mana nak belajar kalau internet tak okey kan. Lagilah nak exam nanti ni. Oh, macam mana. Right. So, okay. Next ialah Kirk effect. Current key. Okay, the final part for BJT. 20 minutes. By the way, everybody, can you write down your name and metric number for attendance? Kadang-kadang saya lupa. Kalau saya lupa, tulis je. Saya dah tua, tak semua benda lupa. Tama-tama banyak kerja. Okay. Okay. Besar sangat ni. Alright. So next is we want to talk about Kirk effect. Okay. Kalau baca ni, tak tahu lah faham ke tak. Saya dulu baca tapi tak faham. So tapi bila faham tak susah pun sebenarnya. Tapi nak boleh faham tu. Okay. Alright. So okay, this is a graph of HFE ni macam beta against IC. So as you increase the collector current, you are expecting the beta to increase. Betul tak? Okay, betul ke tak betul? IC over IB. Right. If everything doesn't change, theoretically, ideally, the way that we understand how BJT works, right? If we increase IC, beta should increase lah, right? Ideally IB shouldn't change. Ideally IB shouldn't change. So that's ideal case. Okay. However, when you do your experiment and you measure the BJT, you will get this graph. So you have at very low collector current to the intermediate to the very high, okay, and against beta, okay. So at very low collector current, what happens is your what happens is at low collector current, you will see the beta increase. Sekejap, betul apa saya kata tadi tu? Sekejap. Nak fikir. Ideally, it should be... Okay, silap. Okay, silap, I'll erase your memory. I will repeat again. Okay. Silap. Okay, so this is the equation for beta. Beta equals to IC over IB. If you don't change, if you don't change IB, okay, therefore and we don't change IC, IB should also be constant. Beta should be constant. If you don't change IB, we don't change the base current, and the collector current we don't change, beta should be constant. It should be constant. So it means that if you don't change, this is with betul ke saya cakap ni? Rasa macam betul dah. Okay. Let me think for a while. We assume IB to be constant. We don't change anything on the IB. Therefore, for the particular IC, beta should be constant. Okay. The red dotted line shows that the beta should be for a given so beta equals to the red dotted line is the ideal beta where it should be constant. Why it should be constant? Because regardless regarding the change of the I forgot everything. Siapa tahu ke kenapa saya lupa ni currently very little current. Ideally it's not supposed to change. You want the base current to be constant, you want the beta to be constant regardless of the changes of the collector current.
Madam,
Huh?
does from the slide this is for the current gain?
Yeah. So
You said about the Kerr effect, right?
yes, saya tak, ini mukadimah pada ke effect.
Oh, okay.
Dia ke effect kat sini.
Okay. Oh, okay. I see. Okay.
Dia macam mukadimah kepada situ. Okay, so I see. IB should increase accordingly. Therefore, data should be okay. Right. Okay. We understand how BJT works, right? If everything goes well, semua normal and ideal. As we increase the IC, which means that you increase the IE, the IB will also increase. So that proportionately. Are you following me?
Yes.
So if everything works perfectly fine, I repeat myself. I will repeat myself. As everything works perfectly fine, as we increase IE, right? IC will increase. Therefore, IB will also increase because you have more recombination, you have more free carriers. So ideally, beta should be constant because beta is just IC of IB. IC increase, IB will increase for the same amount. Therefore, beta should be constant. Okay, and this is ideal, and this is what we want. We don't want beta to keep on changing with the with the device. However, that's ideal. We use the dotted line here. The beta should be there. However, when we do measurements, we found out that at low current, collector current, the beta is increasing. Or the other way is the beta is actually very low at very low current, at very low collector current, and the beta and the other extreme is at very high current, collector current. Instead of being constant, it lowers, it becomes smaller as you increase the collector current. Now the question is why? Okay, ideally it's supposed to be like this. This is the ideal region. Okay, this is the ideal region where the beta is constant. But in real life, it doesn't happen like that. Okay, that's why we engineers and scientists, we need to think of a reason when we found something. So at low current, okay, at low collector current here, recombination current dominates. Do you understand what recombination current dominates means? Kita hari tu tak pernah cerita dah recombination. Pernah saya cerita recombination current? Ke tak? Dari sisters, are you following me? Okay. You know what recombination current is? Huh? Kat mana we have recombination current?
Forward bias.
Okay, forward bias. Where does the recombination current occur? Kat mana dia? Kat emitter base.
Base.
Yes, base. Remember, we want to reduce the doping of base because we want to reduce the recombination. And the base current is actually due to recombination, right? So, okay, at very low collector current, when we say very low collector current, it also means at very low emitter current. It means at very low bias, forward bias, right? At very low forward bias, what happens is, I'm going to draw. You have emitter, you have the base, you have the collector. Okay, at very low collector current. Okay, so it means that you still this equation still happening, right? It means that the emitter, you have electrons flowing through here, some will recombine and then be replaced, and mostly will be collected. Now, at very low collector current, it means that IE is also low. Okay, IE also low. When IE is also low, it means that the electrons that comes here, the base, that proportionately to the overall collector current or the overall total current, there will be more recombination in the base, especially when you have I was thinking whether the defect will make it even worse. No, will make it higher. Okay, so so basically, let me repeat. As at very low collector current, it means the emitter current is also low. Okay, so it means that when electrons are traveling, so electrons are diffusing from emitter to the base, proportionately, many will be recombined here compared to the one being collected. Okay, so that's why at low collector current, IB is not constant because in proportion, there's more recombination compared to the overall collector current. And also it's due to the, I think, due to the defect. Let me think. I lupa lah, how does it, the defect in the base affect at low current. Oh, okay. All right. Remember last time when we talk about the defects inside a semiconductor, inside a p-n junction, what does the defect do to the current? When we have defect inside a p-n junction, what does the defect do in terms of the electrical characteristics? Do you understand my question? Defect?
It raises the Fermi level?
No.
It produces a trap.
Yes, so it produces trap. So what happens then?
Which makes the current to pass through easily. Step by step. Yeah.
Right, so you have more of the generation current. Okay, generation current. You have more current. Okay, therefore, in the base, at low collector current, so meaning at very low bias and very low number of free carriers moving, if we have defects, it will be more it will be more dominating. China is an explain so that you understand. So it means that in the base current, in the base here, at low, you will have defects in the base, and this defect will increase the current, right? Remember, this is actually increasing the current, right? Defect increases the current because it will be easier for the electron to be excited for generation current to be easier. Therefore, it means that in the base, the base current will increase. So it's not constant because it's very low. At high current, okay, apa beza dia? Saya tak faham. Okay, let me see. I give you two example. Satu macam ni. Okay, satu. So CEP. Okay, both have a trap. Kata both have 3 traps. Okay, both have 3 traps, but this is at low IC. This is at high IC or high or moderate IC. I would say high, high IC. Or high IC means high current. When you have a lot of current, the defects will be filled. Ini saya tak pernah cerita lagi. It means that kata kat low IC, dia akan macam ni. Okay, so you have a lot of the trap becomes effective. There is trap, the defect is there and is effective in increasing the current. However, for high, when you have a lot of current, high collector current or any current inside, you have a lot of free carriers. This trap might be filled. Dipanggil fill trap. Okay, what does it do? Basically, trap tu macam lubang kan. But this trap is being filled. There are the carriers inside the trap. So the trap no longer behave like a trap. Sebab dia dah penuh. So it means that for this one, the electron here cannot go to the trap. So the electron will need to go directly like that. Okay, do you understand? So although the trap is the same, because the trap comes from you when you fabricate the device, the number of trap is the same, but the effectiveness of the track depends on the number of free carriers. If you have a lot of free carriers, the track will be filled. So the track no longer dia macam tak berkesan, no longer behave like a track. So because it's a, we call it the field track yang filled, dah penuh. So therefore you can no longer have this mechanism. Okay, so at low current, you have this problem where the defect will be effective. Therefore, the base current will be the base current will be increased, and until, so you can see then it becomes like normal over here, right? Until there will be enough current so that all at this region here, all the tracks are being filled. So along the way, it will keep on filling the track, and therefore you will keep on increasing the base until the track is filled. And this is the region where it's like ideal. The track is there, however, dia macam you dah swamp dia, you dah tutup dia. Faham ke tak ni?
Yeah.
Boleh.
Boleh ya? Okay, that
Boleh.
is happen at low collector current, and that's important. And remember, brothers and sisters, you can use this mechanism everywhere. This when I explain about this region here, this concept of filling of the tracks, it can happen in PN junction. It can happen in any semiconductor material. This concept, but how high or how low, it depends on the material. Maknanya how much current you need to put in order for it to fill. It depends on the material, number one. It depends on number of tracks, how many tracks you have, number two. And it depends on what are the kind of tracks, number three. So different tracks have different characteristics, have a different behavior. So tapi generally it's like that. So when you answer in your final exam, since open book, there's no right or wrong. You just write down what you think. If it's logical, I will give you the marks. Okay? So you need to combine all your knowledge, make sure you can link here and there. As long as it's logical, I will give you the marks. It shows that you are actually thinking and your thinking is logical and makes sense. Okay, so that happens at low collector current. Then the ideal thing happens, no problem, IB increase, IC increase, so beta should be constant. Now the problem is at very high collector current, which is the Kerr effect, which the time is already finished. We'll cover Kerr effect in next class, insyaAllah. Okay, so after Kerr effect next week, we'll do MOSFET. MOSFET sikit je, I will cover very little. I'm not covering the secondary effect. I will just covering how MOSFET works. Okay, untuk next week. Okay, any question before we end? Kalau tak faham, buat tengoklah lagi. And if there's anything wrong that I mentioned, kadang-kadang saya sebut benda lain, saya maksudkan benda lain, you can ask me. Okay, let's end the class. If you don't have any question, kita ada exam, ada quiz minggu depan Khamis ni
Yes, madam.
Soalan on apa? Saya lupa dah. Buat lagi. Soalan on apa? Soalan tu apa?
Laser.
Bukan laser, solar cell.
Okay.
Madam,
yes.
Boleh madam upload tak yang slide untuk kelas sebelum ni?
Slide?
Video, recording untuk yang kelas sebelum ni.
Sebelum ada satu je lah, nampak banyak kelas saya tak upload
Ada 2 kelas.
Baiklah, saya akan buat lepas ni.
Okay, madam.
Alright, saya pun dah dengan tukar laptop pun semua ni, tak tahu. Hopefully saya boleh jumpa lah video tu kat mana. Okay, alright. So, thank you very much. Let's end with the doa. So, one person to make doa. Cepat. Cepatlah kita semua nak buat benda lain ni. Oh, semua tak nak keluar ke?
Madam.
Okay, silakan.
Okay, Bismillahirrahmanirrahim. Alhamdulillah Rabbil Alamin. Wassalatu wassalamu ala sayyidina Muhammadin asyrafil anbiya'i wal mursalin wa ala alihi wa sahbihi ajma'in. Allahumma inna bil iman wa mintal bil iman wa shinal bil iman wa adkhilna bil jannati ma'al iman. Allahumma talna bi husnil khatimah wa la tatam bi su'il khatimah. Allahumma ja'alni minal ladzina yanzuruna al-kitaba nazrah wa ahiratan yahfazuna ma fihi wa yafhamuna bihi wa ya'maluna bihi wa yuballighuna bihi. Allahumma inni stauda'tuka ma 'allamtanihi fardudhu ilayya inda hajati wa la tunsinihi ya rabbal alamin. Allah Rabbana la tuzigh qulubana ba'da idh hadaytana wa hab lana min ladunka rahmah innaka antal wahhab. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina azabannar. Wa sallallahu ala sayyidina Muhammad walhamdulillahi rabbil alamin. Amin amin rabbil alamin.
Rabbal alamin.
Amin ya rabbal alamin.
Happy benar Muhaimin. Kita tutup dengan tasbih kafarah al-Fatihah. Subhanakallahumma wa bihamdika asyhadu an la ilaha illa anta astaghfiruka wa atubu ilaik. Bismillahirrahmanirrahim. Wal 'asr. Innal insana lafi khusr illa alladhina amanu wa 'amilus solihat wa tawassaw bil haqq wa tawassaw bis sabr. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam. Okay, madam.